In this series of basic algebra, the first video that we are going to discuss is on real number system. This is nothing new, alright, but for some it may be a refresher. In the real number system, the first set of numbers is set of natural numbers n, 1, 2, 3, so on and so forth up to infinity, which are also known as counting numbers, as they are used to count the objects or things. They can be plotted on a number line 1, 2, 3, 4 up to infinity. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. By adding 0 to the natural numbers, we get set of whole numbers w, 0, 1, 2, 3 up to infinity, and we plot 0 at a distance 1 unit to the left of 1, and that completes our whole set on the number line. To the left of 0, at a distance of 1 unit each, we plot 1, 2, 3, etc. and give them negative signs up to infinity, and that gives us set of integers from negative infinity -3, -2, -1, 0, 1, 2, 3, so on and so forth. So set of integers consists of negative integers and whole numbers. Between these integers there are numbers known as rational numbers denoted by q. They are in the form of p upon q, where p and q belong to set of integers and q is not 0. For example, 1 upon 2, where 1 and 2 are integers, is a rational number, and it is also known as proper fraction because here numerator 1 is smaller than denominator 2. To plot 1 upon 2 on this number line, we make two equal parts between 0 and 1 and take one part that gives us 1 upon 2. 3 upon 2 is a rational number where both numerator and denominator are integers. This is an improper fraction because here numerator 3 is greater than denominator. 3 upon 2 can be written in the form of an integer 1 and a proper fraction 2. One integer 1 upon 2. So it is also known as mixed fraction. 3 upon 2 can be plotted by making two equal parts between 1 and 2, and this will be 3 upon 2. 3 upon 2 in the decimal form will be 2 ones are 2 and 2 fives are 10, known as terminating decimal form, but 2 upon 3 will be 0.666 up to infinity, known as non-terminating decimal form. We can plot 2 upon 3 by making three equal parts between 0 and 1 and taking two parts from them. So this is representation of 2 upon 3. Negative half will be here. Negative minus 3 upon 2 will be here. Integers -3, 2, 0, etc. are also rational numbers q because they can be written as -3 upon 1, 2 upon 1, 0 upon 1, etc. where both numerator and denominator are integers. 11 upon 4 is 2.75, which is a terminating decimal where the decimal representation ends. 45 upon 12 is 3.75, is also a terminating decimal because the decimal representation ends. But 22 upon 7 is 3.142857, 142857 etc. up to infinity, where the group of 142857 repeats up to infinity. So this is a non-terminating repeating decimals. 7 upon 3 is 2.3333 up to infinity, which is also a non-terminating repeating decimal. 12 upon 45 is 0.2666 up to infinity, which is also a non-terminating repeating decimal. These non-terminating repeating decimals are also represented as 3.142857, and a bar is drawn on this repeated group of numbers. Similarly, this 2.3333 is also written as 2.3 and a dot on the repeating digit, or 2.3 and a dash on the repeating digit. This 0.2666 is also written as 0.2 and a dot on the repeating 6, or 0.26 and a dash on the repeating 6. So a rational number may either be a terminating decimal or a non-terminating repeating decimal, like these rational numbers. For plotting irrational numbers, first we draw a number line. On this number line, we plot point 0, and at a distance 1 from 0, we plot number 1. At number 1, we draw a perpendicular of length 1. We name this perpendicular 1A. Then we join 0A. Since triangle O1A is right triangle, distance OA will be, by Pythagoras theorem, square root 1 square plus 1 square, square root of 2. OA as radius and O as center, we will draw an arc from A which cuts the number line at point root 2, because distance O root 2 is root 2. Next we draw perpendicular at root 2 of same length 1, and we name this point B. Next we join O and B. Now in right triangle 0 root 2B, length OB will be square root of root square, which is 2, plus 1 square, which is 1, that is root 3. Now O as center and OB as radius, we will draw an arc which cuts the number line at point root 3, and this distance 0 root 3 is root 3. We can continue with this process and plot root 5, root 6, etc. on this number line. On the left hand side of 0, using the same technique, we can plot minus root 2, minus root 3, etc. As we can see, all these numbers are irrational numbers because they are not rational, and hence can't be written in the form P upon Q, where P and Q are integers. So set of real numbers Q and set of irrational numbers, say Q dash, together make set of real numbers R. We know that 2 is less than 3 because 2 is to the left of 3, but minus 2 is greater than minus 3 because minus 2 is to the right of minus 3. So therefore, when we change signs, the inequality reverses. 1 upon 2 is less than 3 upon 2 because 1 upon 2 is to the left of 3 upon 2 on the number line, but minus 1 upon 2 is greater than minus 3 upon 2 because minus 1 upon 2 is to the right of minus 3 upon 2 on the number line. So when signs are changed, inequality is reversed between two rational numbers. 2 upon 3 is a rational number in P upon Q form, which is 0.666 up to infinity, or it is 0.6 bar. Now suppose we are given 0.6 bar only and we want to find this decimal form into P upon Q form, then how to find that? Now here, first of all, we assume this 0.6 bar to be x. Next, we see that only one digit is repeated after infinity. So we will multiply this statement by 10. So this will be 10x is equal to 10 multiplied by 0.666 up to infinity. This will be 6.666 up to infinity, which we write as 6 plus 0.6 bar, which is 6 plus x, because 0.6 bar is x. So we have 10x is equal to 6 plus x, 9x will be 6. So x will be 6 upon 9, 2 upon 3, which is exactly what we have here. Next, suppose we want to find out 2.23, 23, etc. up to infinity in P upon Q form. We write this 2.23, 23 up to infinity as 2 plus 0.23, 23 up to infinity. We name this number 1. Now for this 0.2323 up to infinity, we assume x. So x is 0.2323 up to infinity. Now here a group of two digits 23 is getting repeated. So we multiply this by 100. So this is 100x is equal to 23.23, 23 up to infinity. This we write as 23 plus 0.23, 23, so on and so forth. So 100x equals 23 plus, for this we write x. So 99x will be 23. So x will be 23 upon 99. Now we will substitute 23 upon 99 for this 0.2323 up to infinity. So that gives us 2.2323 up to infinity equals 2 plus 23 upon 99, which is 221 upon 99. So this is P upon Q form of this form of rational number. We have seen by doing specific calculations how we can convert rational number 0.666 up to infinity in the P upon Q form as 2 upon 3, or decimal form 2 upon 2323 up to infinity in the P upon Q form as 221 upon 99. Now we will check whether we can write this decimal form 0.666 up to infinity directly. So for that, first we write the digit which is repeating in the numerator upon, since a single digit is repeating, so in the denominator we will subtract 1 from 10. So that gives us 6 upon 9, 2 upon 3. Now this is exactly what we have got here for 2.2323 up to infinity. First we write this number as 2 plus 0.2323 up to infinity, which is 2 plus, here a two digit number 23 is repeating, so that we write in the numerator upon, for two digit number we will subtract 1 from 100, so that will be 2 plus 23 upon 99, which is 221 upon 99, exactly same as we have got here. Now we will try a new number 3.693693 up to infinity. This first we write as 3 plus 0.693693 up to infinity, which is 3 plus, here a three digit number 693 is repeating, that we write in the numerator upon, for a repeating three digit number we will subtract 1 from 1000. That gives 3 plus 693 upon 999 dividing by 9. This will be 111. 9 sevens are 9 sevens are, which is 3 plus 77 upon 111, 410 upon 111. Now this is P upon Q form of non-terminating repeating decimal form. Other than rational numbers, there are numbers which cannot be represented in the form P upon Q, where P and Q are integers and Q is a non-zero integer. Such numbers are irrational numbers. In short, the numbers which are not rational are irrational. For example, square root 2, square root 3, square root 5, square root 11, etc. are all irrational numbers because they cannot be expressed P upon Q. We can plot these irrational numbers on a number line where we draw a perpendicular A1 of length equal to 1 unit. Next we join OA. Now with radius OA and center O, we draw an arc which cuts the number line at point root 2 because distance OA according to Pythagoras theorem is square root of 1 square plus 1 square root 2. For plotting root 3, we have to draw another perpendicular P root 2 and join OB. Now with radius equals OB and O as center, a curve is drawn which cuts the number line at point root 3 because according to Pythagoras, OB is root 2 square 2 plus 1 square 1, which is root 3. By using the same technique, we can plot root 5, root 6, etc. on this number line. For negative irrational numbers, minus root 2, minus root 3, etc., we have to apply the same technique to the left of 0. Now all the rational numbers Q together with all irrational numbers, say Q dash, forms the set of real numbers R. Here rational numbers Q and irrational numbers Q dash are disjoint sets because there are no common numbers between them. So no rational number is irrational and vice versa. For proving root 2 is irrational, we will use method of proof by contradiction, in which we start by assuming root 2 is not irrational. So we can write it just like a reduced form of rational number a upon b with no common factors. So a is root 2b. After squaring, a square equals 2b square, which means a square is even by presence of this 2, and by rule, if a square is even, a is also even. We name this 1. Now since a is even, we write it as a equals to k, where k is some other integer. Squaring, we get a square equals 4k square. Since a square is 2b square, we write 2b square equals 4k square, b square equals 2k square. This 2 makes b square even. By rule, this implies b is also even. We name this 2. From 1 and 2, both a and b have common factor 2. But this contradicts the fact that root 2 has no common factor. This means our assumption that root 2 is not irrational is wrong. Hence, otherwise, that is, root 2 is irrational is correct. Hence, root 2 is irrational. Most common irrational number is pi, which is the ratio of circumference c of a circle to its diameter d, whose value is an irrational number 3.141592 654 up to infinity. For calculation purpose, we use 3.14 or 22 upon 7, which of course are rational. Unlike rational numbers, decimal representations of irrational numbers is non-terminating and non-repeating. Decimal value of root 2 is irrational number 1.41421356 up to infinity, where this pattern is non-terminating and non-repeating type. Decimal value of root 3 is 1.73205081 up to infinity, again non-terminating, non-repeating type. 3 is rational. Adding irrational root 2 no longer keeps it rational, but now 3 plus root 2 together becomes irrational. So, addition subtraction of irrational and irrational is always irrational. Irrational 5 minus root 3 and 5 plus root 3 are called conjugates of each other. Conjugates are obtained by changing the sign of irrational part. Adding conjugates 5 minus root 3 plus 5 plus root 3 gives us 10 irrational number after cancelling root 3. But subtraction of conjugates gives us irrational number minus root 3 after cancelling 5. Conjugate of minus 10 minus root 5 is minus 10 plus root 5 after changing the sign of irrational part only. Adding them will give us minus 10 irrational number, while subtracting will give us plus minus 2 root 5 irrationals. We can add root 2 and root 2 to get 2 root 2, an irrational number, but root 2 minus root 2 is 0, a irrational number. Adding root 2 and root 3 cannot be simplified further, and these two numbers together gives us an irrational number. Conjugate of root 2 plus root 3 is root 2 minus root 3, which after addition gives 2 root 2, and after subtraction gives 2 root 3, an irrational number. 2 plus root 3 and 2 minus root 3 are conjugates of each other, and their multiplication will be 2 square minus root 3 square, 4 minus 3, 1, which is a rational number. Root 3 plus root 5 and root 3 minus root 5 are conjugates of each other, and their multiplication is root 3 square minus root 5 square, 3 minus 5 minus 2, which also is a rational number. So multiplication of conjugates of a rational number gives us a rational number. Root 2 multiplied by root 2 is root 2 square 2, which is a rational number. Viewers, if you like this video, please click the like button. Share this video with your friends and classmates. Subscribe to this channel. Post your constructive comments to make the videos better. See you in the next video. Until then, keep watching Number Collage. Thank you.